Hey everyone, my name is Luis, and for my midterm project, I selected this Recruit Restaurant Visitor Forecasting Competition on Kaggle. This is a competition that was put on by Recruit Holdings to try and predict the number of future restaurant visitors for several stores in Japan. For data, Recruit provided several data sets that included reservation data, holiday and date data, some store information, and this was all aggregated from two sources. So the first was Hot Pepper Gourmet, and the second was Air Reggie. So these are two online sources that are similar to Yelp and Square, which my American colleagues may be more familiar with. Because there was so many various data sources, the data wrangling cleansing tasks were pretty significant. I piggybacked a bit from the public kernels, but definitely spent a lot of time on feature engineering, and I'll get into that a little bit more in a minute. For the data wrangling and cleansing, I created a utility Python package that I call from my main Jupyter packages, Jupyter notebooks. And as you can see here, it iterates through the various data files, adding features and stitches them all together. So it adds features that may be helpful, such as day of the week, month, year, week of the month type variables. As well as does some lagging and differencing since we're dealing with time series data. Here I do up to a week's worth of lags and differences. Another significant number of the features have to do with the restaurants themselves. So here we have high-level aggregations by the restaurants of the min visitors, mean visitors, median, and so on. So let's go into the exploratory data analysis to see how I landed on some of the other features. So here I import that Recruit utility package. It allows me to import the data, generate training and testing data sets. So here we inspect the data, and it shows that the training data has over 250,000 records, and the test data has about 32,000 records, with 74 features or variables each. At first I selected this competition because I thought it would be heavy on time series analysis, something I'm weak at. But it turns out the data is a conglomeration of several noisy time series. There's actually more than 300 unique restaurants here, each with their own time series, as we can see in this graph. So in order to do a more straightforward ARIMA analysis, I would have to somehow aggregate all of these time series and then disaggregate when forecasting. And for this reason, I decided to use mainly linear and tree-based and machine learning techniques. Right here we see an aggregation of all the restaurants with their mean visitors over time. It does appear that there's some seasonality here, both weekly and yearly. And to address this, I difference the time series, which we see here. So that definitely looks better. It looks more centered around 0. And here's another example here. This one's difference now 7 days. Looks more like white noise. Also, some geographic information was provided. Here we can see an overlay of all the restaurants over Japan. And the size of the circle corresponds to the number of visitors for those restaurants. Due to this, some clustering was done to try to provide some predictive capability to the location, and also to cluster similar restaurants with each other. So this graph is the same. The size of the circle is the number of visitors, but now we see the colors are the colors of the cluster. All right, so now let's take a closer look at the target variable and the predictors. So this is the target, and we can see that there's some pretty significant outliers here, which is shown a little bit better when we take a log of the visitors. Due to the outliers, just from here on out, I start using log visitors, log transformation for all the analysis. Also, we plot a parallelogram to show the correlation between numerical variables and the target. So here, log visitors is the target. We can see that these aggregated store visitor information is going to be pretty predictive. And we can also see that there's probably going to be some multicollinearity between some of the other variables. Now I also want to see how predictive the categorical variables are going to be. So here's some box plots that give us a sense of how these are correlated with log visitors on the y-axis. And this is, for example, day of the week. So we can see that day 5 probably has the highest median of log visitors, and that there is some relationship here between the day of the week and the log of the visitors. Of course, I do this for all the categorical variables: week of the month, year, month, day, and some others, holiday flag. We also have the genre name of the restaurant and the area name of the restaurant. And now we're getting pretty noisy here with the actual air store ID, the ID of the restaurant. So, switching back to outliers and potential multicollinearity, I fit a pretty straightforward and simple OLS regression to get a sense of the multivariate relationship between the numerical variables and the target. Unfortunately, the influence plot never was able to print, but I did get a sense of the VIF values. And here we can definitely see some huge VIF values, inflation factors between variables. So we expect there to be some sort of variable selection or variable reduction going on here. And another thing to note actually is that the R-squared is pretty good for this OLS regression. So already we're capturing a lot of the variability in the response, which is good. Another thing that I noted was that this OLS regression is not doing a very good job with very high visitors. So here we have the predictions on the x-axis and the actual visitors on the y-axis. And some of these very high outliers aren't really being well predicted by the model, which got me to thinking maybe there's a way that we can identify these values as a large party. So I assigned everything that was greater than 120 to large party in the training data. Then I took a look at the various categorical variables to see what relationship they had on this large party. So we see day of the week 5 and 6, weekends we see larger parties, week of the month, some of these months see a lot larger parties. So there may be some predictive capability here. And to that end, I fit a logistic regression to see if I can predict which days and stores are going to get a large party. So we have a pseudo R squared of 0.36, and our area under the curve makes us believe that yes, area under the curve is 0.95, so we probably can predict whether we're going to get a large party. And then we can add this feature based on existing features to the test set as well. So that is another way that we engineer the features. Next, I wanted to get a sense of the differences between the training and the test data. So I combined the tests and the training data sets, and then in a factor plot, show the differences. See how many more of any type of category. So for example here, we have data set equals train, data set equals test. On the left we can see we have 2016 values, on the right we don't. That's to be expected. The test set was only for April and March of 2017, but still we can see that there is a difference in the types of variables that we're going to get, the types of values. Some of the more interesting ones are that the area names come in different percentages, and the genres, the store IDs, are represented differently in the training and test. So in order to just get ahead and try to avoid overfitting, any area that isn't represented in the test was removed from the training data set. Very good. So moving on to some time series statistical tests, I want to kind of try to understand what the autocorrelation is in these time series, and also test some stationarity. So I set up a Dickey-Fuller test and take a rolling mean of the averaged time series of log visitors. And it does seem to have some movement here. However, interestingly, the p-value rejects the null hypothesis that a unit root is present. Okay, well, still, I go on to difference that mean of time series, and it definitely looks a lot better. The p-value goes down as expected. But I'm still a bit curious about that result. So I test another type of test, the KPSS test. This actually tests the null hypothesis that the time series is stationary, so the opposite. And we get the opposite result. So in a couple of these, we do reject the null hypothesis that the time series is stationary at lags 1, 2, 3, 4, all the way up to 16 at alpha level of 5%. And then when we difference and run the same test, we get much better results. All of these say 0.1, but they're really below 0.1. It's a little bit hard to read, but this is the statistic and this is the p-value. So this result at the 5% level would not reject the null hypothesis. Now our differenced time series is stationary. But still, it was a different result from the Dickey-Fuller test, so just to be complete, I went and did the Young box test. This tests the null hypothesis that any of a group of autocorrelations are different than 0. So more similar to the Dickey-Fuller test. And again, these results are a little bit hard to interpret, but these are the test statistics and these are the p-values. All of these p-values, very small, reject the null hypothesis that there's autocorrelations. So again, I get even a different result. However, looking at the ACF plots and the PACF plots, I'm pretty confident that there does seem to be some ARMA effects here. All of these values, especially in the ACF test, are significant. Great. Let's move on to predictive modeling. So again, we prepare for modeling, we import everything, build a train and test. Get all our categorical predictors, numeric predictors, and target columns. And first, we fit an OLS. Now our R-squared is pretty low, especially compared to the one that we fit earlier. But we already know that there's going to be some issues of multicollinearity here. So we work through these issues and remove any of the predictors that are highly correlated with each other. And again, get back to our nice 0.932. We cross-validate this, and a point of note here, cross-validation for time series is a little bit different. I found this out, and I recommend going to this blog by Rob Hindman that discusses time series cross-validation. And basically, what we want to do is we actually want to, instead of just taking folds all separate from each other, we want to build up our cross-validation set in folds. So it's a little bit different than just the straightforward k-folds or leave one out cross-validation. So to that end, I built in our utilities package a training time series cross-validation that loops over our time series split. Cool. So now we can get our cross-validation results. And for our OLS regression, we get a 0.643, which is our baseline from here on out. I'm not sure that that even made it onto the leaderboard of Kaggle, but it's a good start anyway. So my next step was to use lasso regression to help, in addition to selecting variables manually, to select variables using regularization. So I test alphas in a range from 0.001 to 1, incrementing by 0.005, and here we can see the results visually. At very low lambdas, it turns out that our root mean squared log error is minimized. And it's minimized at 0.24. So that's much better than we got with our OLS regression, but at this point I'm a little nervous that I've started overfitting. But we'll move ahead into tree-based regression. The first tree-based algorithm that I run is a random forest regressor. And again, we cross-validate the results, and our root mean squared log error goes way down. The last model that I've selected here is a gradient boosting using light GBM. There's some documentation here and a quick overview. That's pretty good at this link. But our CV results don't get much better. They don't get better at all from the random forest, actually, which makes me think that I need to tune some parameters. But at least we can look at the predictions from that light GBM and see that they're quite good. Here we see a split where our algorithm has picked up the large party and is now fitting those a lot better. There's still some errors here, 800 to 320, but still much better than before. So instead of tuning parameters using cross-validation or manually, and also in light of the worry of overfitting, I move now to auto machine learning using H2O. This is a pretty interesting technique. This was the first time I'd used it, and it was pretty simple to set up. So basically we initialize the H2O cluster that initializes locally, and we pull in an H2O frame which can be built just straight off of a pandas data frame, and set up the max runtime and put it in. Just two parameters here, the y variable, the target variable, and the data frame, and let it go. And we get a pretty interesting result. So it'll run multiple models. Here's a list of all the models that it ran the last time I ran it. So we have some deep learning models, some gradient boosting machines, some generalized linear modeling, and then it stacks a lot of these in an ensemble to pick the best parts of these various techniques. Also, we can get some really great output. It tells us, for example, this stacked ensemble of all these models used let me see if I can find here we go. So this ensemble, stacked ensemble, used these coefficient magnitudes with all of these different learning models in combination to get the best result. It also has pretty significant cross-validation results. Here's a summary. It shows you the metrics of each cross-validation run, but here's a summary of the cross-validation results with a root mean squared log error of 0.018. That's pretty good. This probably isn't the best model that I used in the competition. And the competition just finished, so we'll see how I do. I was about 0.05 points off the pace for first in the public leaderboard, but I know things will probably be different when the private one comes out. So anyway, that's my project, and I'm looking forward to hearing more from all of you. Good luck.